Hello! Today we implement the classic game of Tetris in Python. If you want, you can watch my other video where we also do it in JavaScript and I explain everything step by step. You can download the whole project from GitHub, and the only requirement to run it is to install pygame, so use this command in your terminal and you can start. Okay, so firstly let's create all of the shapes. You can see them on the right hand side. And this is the representation we'll use, so just two-dimensional arrays that are always squares. 1 to say the block is there, and 0 to say it's empty, and that's it. Okay, so we got all these 7 shapes. Time to define the config. This will be all the constants that we want to reuse in our project. Firstly, let's define color per each shape. Then the color of the sidebar border. The color of the empty block. Font color. Background color. This will be the game over overlay, which we will display as black, but with a small transparency, so the alpha of 200. The grid size, the gravity, the initial speed, the acceleration every frame, and also the threshold when it actually drops the block size and sidebar dimensions. Okay, let's define a single piece class. So this is the piece that we move all the time in the game. Obviously, it has its own shape, and the shape is defined by shape ID, which will store to know the color of the shape, even as we rotate the shape. We have the position, so just a random X on the board. And the Y is always 0. Let's create a method that allows to move the piece. So change its X and Y coordinates. So let's also create a method that allows us to rotate the shape. It will return a completely new two-dimensional array with all of the original elements, except as you can see the indices will be transformed as in the image on the right hand side. And to do so we can simply use list comprehension and target each original element, except change the indices. And that's it. Okay, so now that we got the piece, we can also define the gravity class. It's very simple. We just want to, every few frames, we want to drop the block by 1. And we need to keep the track of the progress that it does. And also have some sort of speed so that we can progress it throughout the game, so that it becomes more interesting and difficult. And in the method update progress, we of course increment the speed according to the delta time, how much time has passed since the last frame. Similarly for the progress, we update it according to the speed and time. And finally, if we hit the threshold, we return true to signalize that the piece should drop, and false otherwise. That's it. Now the most important class, which is the grid. This will represent this two-dimensional array or matrix of all the blocks that are already attached to the screen. And of course we need this two-dimensional array. This is how we can define it with the list comprehension. All of the blocks will be empty initially. We also need a method that tells us if we can place a shape onto the grid, so at any position, so that we will know if we can move the piece to the left, to the right, if we can spawn it initially, if we can rotate it, if it didn't hit the floor. And the idea is very simple. Just go through every single block in the shape and compare it against the grid. So if its X or Y dimension are out of the grid, of course we return the false immediately. So let's do it. This is the wall collision. Let's also handle the floor collision, which is when we hit the floor, so it's the Y index. And finally, let's check if the place in the grid is actually an empty block, because otherwise we cannot fit the shape and we return false as well. And finally, if all of these conditions are never met, This means we can fit the shape, so let's return true. And that's one of the most important methods. When we hit the floor, we need to lock the piece into the grid, which basically means copy all of its blocks into the grid and take into account the color of the shape, which we store with shape ID. So again, we go through every single block in the piece. We check if it's solid, so we represented it with 1, and basically just find the position in the grid using the piece position and assign the shape ID. Okay, now the most complicated algorithm, which is clearing all of the lines. The idea is very simple. We go through every single row starting from the bottom, and if it's a complete line, if it's full, we keep track of it and increment the number of cleared lines. And if it's not, that means we need to drop the current row by the number of already cleared lines. So the first row we get nothing to do because it's not full, we don't drop it. The second row is full, so we keep track of it. The third row is full, so we already have 2 cleared lines. Then we have a row that is not full, so we drop it by 2. Then we again have cleared 3. Then we shift by 3, shift by 3, shift by 3, and so on and so on and so on until we reach the top. And all this area is surely correct, but here we need to ensure that these lines are empty as well, because 3 lines were cleared. And that's the entire algorithm, and this is the result. So let's code exactly what we just described. And we will keep track of the cleared lines, go through every single row, but in the reverse order, so starting from the bottom. And now, if every single block is non-empty, meaning the line is full, then, as we said, we'll keep track of the cleared lines, so it's incremented by 1. Otherwise, if we already cleared some of the lines, that means we need to shift the current row and push it down by the number of cleared lines. And finally, we need to ensure that the top lines are shifted as well, by that I mean cleared. And to do so, we just empty all of them, because they are guaranteed to be empty by the definition of our fall. And let's return the number of cleared lines, and that's it. Okay, so we got all the pieces needed to complete our game state. So let's define the class that holds all of our game data. This is basically the definition of game state. All the data that is relevant at any point of time to our game. So we have the grid, we have the piece, we have the gravity, and we also store the next shape ID. Let's also store if the game is over. Of course, it's false at the beginning, and also the score, and likewise, it's just 0. And that's it. That's our entire game state. So we got all of the game state. Now it's time to render it. Let's create a class GameView where we will handle all of the rendering for our game. So the most important method will be just the render of the game state. Let's define all of the constants that will be useful during the rendering. So of course we need to know exactly the grid size. Similarly, the sidebar dimensions, so that we can easily render content there. And by having all this, we can already define the entire game area. And this will be useful to initialize the window with the specified dimension. So we can already do it inside of the initDisplay method. This is how we basically initialize the window in pygame. And you can also already prepare the font that we will use for all the text. I always recommend some monospace fonts such as Monaco. Okay, we have the state, we have the view, time to define our game class, where we will run the game loop. We will start our game by calling the method start, but in order to do it, we need to define all of the instances such as the state. So for that, I suggest always to create a method such as getInitialState, which will allow us later to restart the game state. And we have the grid, we have the piece. We need a random shape ID, so let's define a method for it because we'll reuse it. And this is of course based on the number of all the shapes we have, which is 7. Right, I keep forgetting about the self. We have the gravity as we defined it, and also the shape ID for the next shape we'll have on the screen. Let's also initialize the view. And now about our start method. So let's set the caption of the game window to Tetris. Let's use key set repeat, which will allow us to repeat our inputs by holding the key. Let's use the clock so that we can track the time to have the difference between each frame. And now the game loop. This is the reminder how it should look like. So we need to collect all of the inputs. Let's define a boolean that will help us to break the loop from within it. And let's quit the pygame right after the loop is done. Delta time is the difference between the frames. We clear all of the inputs before each frame because we will use the repeated behavior and collect all of them on demand. So, okay, if the event in the game is quit, then we just stop our loop. And if the event is key down, that means our input is being activated either by pressing it once or holding it for 400 milliseconds. For now, we skip the step with updating state and just render the initial state as it was. And let's also check if our inputs are handled properly. And to initialize the game, we just call the method start on the object. Okay, I did a couple of mistakes that make it impossible to start it. Let's give it a try again. Okay, also grid rows is incorrect because I didn't import it. And now the video system not initialized, so it is a problem again because I didn't init pygame. And finally, I forgot about the self inside of the render method. And now if we run the project, yeah, we got our window, it's completely empty. And as you can see, as I'm pressing the buttons, the set with the inputs is updated. Okay, so let's try to actually render something, a single block, which we'll use for our shapes, for our grid. And this is done with the screen fill method. And we shifted by 1 in the size so that it's a little smaller, so that we have this nice grid. And let's actually give it a try. So here I used the wrong color of 0 and 1, so it's not necessarily the best test. And remember to also add the background to our entire screen. And finally, flip allows us to actually render our bitmap. And okay, it seems to be somewhat working. Let's not waste any more time on it and define draw shape, which will render any shape we'd like. So the current shape, the future shape. This is how we can define it. And again, we just have to iterate the entire two-dimensional array of our shape. So every single row, inside of the row, every single block, if it's solid or not, 1 or 0. And if it is solid, we of course render the block using the colors we have defined in our config. Okay, so let's use it to render the current piece on the screen. So we have to pass the shape, we have to pass the shape ID so that we know the color and the position multiplied by block size so that it's exactly where it needs to be on the screen. And seems like we did a mistake. So let's look into our implementation again. And as you can see, I passed the wrong index to the y coordinate. Let's try it again. Now we can draw the entirety of our sidebar, which shows the next shape and also the score we have. So let's start by drawing the border between the grid and the sidebar. We already got dimensions for all of it. Then let's draw the next shape. Similarly, we pass the shape, we pass the shape ID for the color, and we pass the position that we would like to render it at. For rendering text, we use the font render method. It creates a new surface for us, which is like a bitmap. To actually render this surface, we have to use the blit method, so add a bitmap on top of our display bitmap. We do exactly the same for our actual score value. Let's pad it with 0 so that it always has 6 digits. Just looks better. And exactly the same blit so that we actually render it on our game surface. And let's call our method with the state we got. Awesome. Now let's draw the entire grid, so all the blocks that were already attached on screen. And to do so again, we go through every single element, but this time in the grid matrix. We check the color because this is what we store in the grid, and we use -1, so block empty if it's not filled yet. Based on it, we decide the color, and again we just draw the block in that position. Let's call it at the beginning. And you can see all of the empty blocks, but now we can actually modify the state. Remember, you can always do it. That's the beauty of having everything in a single state variable. We can just artificially insert some of the blocks into the grid matrix. And you can see all of them being rendered here. So it definitely works. Let's clean it up and go back to our rendering. Similarly, we can fake that our game is over by just setting isGameOver to true. And thanks to it, we can test the rendering of the game over overlay. So let's implement it. And here we just want to display this transparent rectangle on top of our grid. And to do so, we create a new surface again, set alpha according to our value. And again, we use blit to just render this bitmap on top of our game bitmap. Let's also add the text, similarly as we did earlier, to say game over. We can target the center of this surface by using getRect centerX. And thanks to it, we can render this text exactly in the middle of the grid. And let's see if this works. Oh, right, we didn't call the method. Let's render it only when the game is actually over, and that's it. It seems to be working just fine. Okay, so let's go back to our game and clean it up. Similarly, let's clean up the printing of the inputs, and time to add our update phase of the game, which is reacting to the inputs and the delta time, so the time between the frames. So let's implement this method, and now we will just try to handle every single input, even without the complete code. So if the game is over, we do nothing, so we can return, and the only action possible is that our input is key R, and if so, we can just reset the game state because we have a method for it, and that's about it. Next, if we press left, then we will run the method which we don't have yet to move the piece by -1 in the x coordinate. And similarly, of course, if we press right, then we move our piece by 1 in the x coordinate. And then when we press the up key, then we rotate the piece. Again, we don't have this method yet. When we press down, we will also move the piece by 1 to the bottom, but this will be a separate method because a collision may happen and we need to handle it properly, the piece landing. And finally, the space is the same as above, except we will do a complete loop until moving the piece down is possible. We'll just allow it pass because the empty loop body is not possible. And finally, let's update our gravity progress, and it returns true if the piece should drop. So again, if it does, then we call our same method move piece down. Okay, and this is our entire game logic, and now all we need to do is implement all of these methods. So let's go about it, starting from the move piece. So we have the coordinates by which we move. And now let's grab the current piece, and we need to check if it's even possible to move. And if you remember, we defined a method if the grid can fit the shape. And here all we're doing is passing this very same shape our current piece has, except with the coordinates to which we want to move. And if it's possible, then we move the piece because there was no collision. And that's about it. And let's just return this because we will use it for other purposes. Next method, rotate piece. And here we will do something very similar. So given the current piece in the state, we return a new shape using piece rotate. This is the method we already defined earlier. And now let's check if this rotation is possible, because sometimes the rotation itself may cause the collision. So again, we use the same coordinates but a different shape and check if the rotation is possible. If so, we just update the shape of our piece. And actually we don't need it, but we can return if the rotation happened. Okay, next the method to move the piece down, and it's a little bit different than moving left and right. First of all, let's reset the gravity progress so that it doesn't immediately drop again right after we press the key down. Second of all, let's see if we can actually move the piece. So this is similar to what we always do. But now if there was a collision, we have to handle the piece landing. Whether we hit the floor or hit other bricks, we have to handle it. And again, let's return if we actually did move so that we can do this loop. And here I realized I didn't put the DT into gravity progress, so let's do it. We need to update everything according to the time as it passes between the frames. And now, handle piece landing. We have to do quite a lot here. First of all, let's grab the entire state, and first of all, let's lock our piece into the grid because it can no longer move. Second of all, let's see how many, let's clear the lines and see how many of them were cleared. We already have a method for it, and let's add it to the score. Next, let's generate a new piece using the next shape ID so that it's fair. And if we can still fit this new piece onto the grid, then we do it, and this will spawn the new piece and also generate the next shape ID. And if not, that means the game is over. And now let's look into our update method. That's all of it. We listen to all the inputs and react accordingly. We can run it. And when I try to play it, you can see I can rotate, I can move. But when I dropped, I realized there is a runtime error. So we called cleared lines as if it's a function, but it's not, it's just a variable. Let's try it again. And now we no longer have an error when we are landing. And let's see if the lines are cleared. Yes, they are, and the score is updated properly. And that's your Tetris, congrats! As always, thank you for watching and let me know what you'd like to see next. Best of luck, bye bye!